A telescope the size of a tennis court is staring at the edge of time, and what it found has physicists terrified. Galaxies that are too big, black holes that formed too fast, structures so enormous they should be impossible. We thought we knew how the universe was born. Webb proved we were wrong. Tonight, we go through every discovery: the surfboard galaxies, the object called the cliff, the force nobody can explain. If you enjoy the journey, like and subscribe. It really helps. Now sit back, turn the lights off. We begin. Building the James Webb Space Telescope nearly killed the project before it ever launched. The idea started in the late 1990s. A group of astronomers wanted a telescope so powerful it could see the very first galaxies that ever formed after the Big Bang. They drew up plans. They pitched it to NASA. And almost immediately, the engineers came back with a problem. The telescope they were describing was physically too big to fit inside any rocket on Earth. The primary mirror alone needed to be over 21 feet across. That is wider than a school bus is long. No rocket fairing in existence could hold something that size. So the engineers proposed something that had never been done before in space. They would fold the mirror, like origami, 18 separate hexagonal panels, each one coated in a layer of gold, thinner than a human hair, would fold up tight for launch, and then unfold in space, locking into position with a precision measured in nanometers. Nobody had ever done this at that scale. The risk was enormous. Then came the cost. Early estimates put the project around $500 million. By the time it launched, the bill had climbed past $10 billion. It took over 20 years from early design to launch day. Engineers called it the telescope that ate NASA's budget. There were congressional hearings, serious talks about canceling it entirely, twice. The launch itself was terrifying. On Christmas Day, 2021, a rocket carried Webb into space from a launch site in South America. Inside that rocket were 2 decades of work, $10 billion, and a mirror that had to unfold perfectly in a sequence of 344 separate steps. Every single one had to work. If even one failed, the whole mission was lost. There was no way to send astronauts to fix it. Webb was heading 1,000,000 miles from Earth, 4 times farther than the Moon. Over the next 2 weeks, engineers at Mission Control watched every step. The sun shield unfolded. 5 layers of a material as thin as a human hair, each one the size of a tennis court, spread out to block heat from the sunday. Then the mirror panels began to move, one by one. Tiny motors pushed each hexagonal segment into place with screws that turned in fractions of a millimeter. The team barely slept. On January 8th, 2022, the final mirror panel locked into position. The telescope was open. It worked. But the hardest part was not the launch. Webb needed to cool down to a temperature colder than most of deep space before its instruments could function. It operates at around -448 degrees Fahrenheit. At that temperature, its infrared detectors can pick up the heat signature of a single bumblebee on the Moon. That sensitivity is the entire point. The light Webb chases is ancient. It left its source over 13 billion years ago. During that journey, the expansion of the universe stretched it from visible light into infrared, a wavelength human eyes cannot detect. Webb was built specifically to catch that stretched, ancient glow. When the first test images came back, the team went quiet. The detail was beyond anything they had predicted. Thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. Ancient light, finally arriving. And what that light revealed was about to rewrite everything. The image appeared on screens at Mission Control in July 2022, and the room went silent. It covered a patch of sky so small you could block it with a single grain of sand held at arm's length. And inside that grain of sand were thousands of galaxies. Some of them smeared into arcs, some stretched into rings, some caught mid-collision with their neighbors, and all of them ancient beyond imagination. NASA called it the deepest infrared image of the universe ever taken. Every smudge of light in that image was a whole galaxy. Some held hundreds of billions of stars, and the light from the most distant ones had been traveling for over 13 billion years before landing on Webb's mirror that morning. President Biden presented the image at a White House briefing before the official science release. That is how significant it was considered. Researchers who had spent decades working toward this moment sat in front of their screens and cried. But here is what made it stranger than it looked. The image showed a galaxy cluster sitting roughly 4.5 billion light-years away. That cluster is so massive, so packed with matter, that its gravity warps the space around it like a bowling ball sitting on a stretched rubber sheet. That warped space acts like a lens. It bends the light coming from galaxies behind it and magnifies them. Webb used this cosmic magnifying glass to see objects that would otherwise be completely invisible. Galaxies that existed just a few 100 million years after the Big Bang appeared in the image as tiny smeared streaks of light, bent and curved by the cluster's gravity into bright arcs. One arc in the image became famous quickly. Astronomers traced its light curve and found the galaxy behind it was so far away that its light had left before the Earth existed, before the Sun existed. It formed when the universe was less than 1 billion years old. What stunned the team was the detail. Earlier telescopes could detect these ancient galaxies, but only as fuzzy blobs. Webb showed structure, clumps of star-forming regions inside galaxies, the texture of stellar nurseries glowing in the dark of the early universe. And then the science team started measuring. They looked at the sizes of those ancient galaxies. They measured their masses. They estimated how many stars lived inside them, and the numbers came back wrong. Galaxy after galaxy in that image was bigger, heavier, and more mature than any model said it should be at that age. These were not the small, scattered clumps of gas that cosmology predicted for the early universe. These were full, dense, organized systems, already running. One researcher described it as finding a city in the middle of a place where you only expected to find wilderness. The standard model of cosmic structure formation says galaxies grow slowly. Gravity pulls in gas. Gas condenses into stars. Stars explode, scatter metals, and the next generation forms richer and more complex. This process takes billions of years. The image Webb sent back showed that at least some galaxies had skipped ahead. They had already done billions of years of growing in a fraction of the time. Nobody had an explanation, and that was only the first image. The deeper Webb looked, the worse the problem got. And the next discovery waiting in the data was something that forced astronomers to say out loud what they had been afraid to say privately. The rules were broken. For decades, cosmologists had a model, a clean, tested, confident model of how the universe began and grew. It went like this. The Big Bang happened 13.8 billion years ago. In the first seconds, the universe was a hot, dense fireball of pure energy. As it expanded and cooled, matter formed. Hydrogen and helium filled everything. Gravity slowly pulled that gas into clumps. Over hundreds of millions of years, those clumps collapsed into the first stars. Those stars grouped into small, messy, irregular galaxies. And those tiny galaxies slowly merged over billions of years to build the large, organized systems we see today, including the Milky Way. The timeline was clear: small and messy first, large and organized later. Scientists built computers to simulate this process. The simulations matched observations beautifully. The model was so well confirmed that physicists called it the standard model of cosmology. It had a name: lambda, cold, dark, matter. It described everything from the temperature pattern of the cosmic microwave background to the distribution of galaxies across the modern sky. Then, Webb started sending data, and the standard model began falling apart, piece by piece. The first shock came from the sheer number of massive early galaxies. A team of researchers ran the Webb data through their analysis tools, expecting to find a small number of unusually bright objects. They found hundreds, Galaxies with the mass of the modern Milky Way, fully assembled, burning with billions of stars, just 300 to 500 million years after the Big Bang. The standard model said this should be nearly impossible. Gravity simply cannot pull that much gas together and ignite that many stars that quickly. The math did not allow it. One astronomer put it bluntly. She said if the James Webb Space Telescope data was right, and it was, then something was wrong with the model. The galaxies in the data were too old for the universe they lived in, like finding a fully grown tree in a pot of soil that was only planted last week. Then came the structures. The standard model predicted the early universe should be smooth. Large, organized patterns in the distribution of galaxies were supposed to take billions of years to develop. Webb found organized chains, filaments, and clusters in the first billion years. The universe had arranged itself far faster than any simulation allowed. Some scientists initially suggested measurement errors. Maybe the redshift readings were off. Maybe the galaxy masses were being overestimated. Teams went back and checked. Multiple independent groups reanalyzed the same data with different methods. The answer kept coming back the same. The galaxies were real. The masses were real. The timeline was real. One team published a paper stating simply that the standard model could not produce what Webb was seeing. Another paper called it a 5 sigma tension, meaning the chance of it being a fluke was less than 1 in a million. The model that explained everything for 40 years had a crack running straight through it, and the deeper Webb looked into the ancient universe. The wider that crack grew, what it found next made the galaxy problem look small. Picture the universe at 300 million years old. That sounds ancient, but on a cosmic scale, it is a newborn. The Big Bang happened only 300 million years before this moment. Stars have barely had time to form. The universe should be full of raw gas, scattered clumps of hydrogen and helium, and only the earliest, smallest, most primitive collections of stars. Tiny stellar nurseries, barely organized, just getting started. Webb pointed at this era, and instead of nurseries, it found cities. The technical name for these objects is massive early forming galaxies, but that label barely captures what they are. These are systems containing billions of stars, fully assembled, running at full capacity, already enriched with heavy elements that took multiple generations of stellar explosions to create. The stars in these galaxies had already been born, lived their lives, exploded as supernovas, scattered metals into space, and seeded the next generation of stars. All of that happened inside the first few 100 million years. One specific galaxy grabbed headlines. Scientists called it JADESGSC 140, but we can just call it the record breaker. It formed just 290 million years after the Big Bang. It was not faint and barely detectable. It was luminous, bright, actively making new stars at a rate so high it would be extraordinary even in the modern universe, let alone at that age. And it already contained oxygen, an element that only forms inside stars that live, die, and explode. For oxygen to be there at that age, at least 2 full generations of stars had to have come and gone already. 2 full stellar generations in under 300 million years. The standard model allowed for maybe the very first stars to be appearing at this point. Instead, Webb found a galaxy already on its 2nd generation of stellar evolution, glowing like a city with the lights fully on. The mass problem compounded things further. These early galaxies were massive. Some weighed in at tens of billions of times the mass of the Sunday. Growing that much mass requires accumulating enormous amounts of gas, converting it to stars efficiently, and doing it at a rate far beyond what physicists thought the early universe could support. The gas supply exists, but the rate of conversion into stars seemed to break a physical limit called the Eddington rate, the fastest that matter can collapse and ignite before its own energy pushes the remaining gas away. The early universe was apparently doing something faster than the physics of gas and gravity should allow. A team of researchers ran these galaxies through every known model: cold dark matter simulations, modified gravity models, adjusted star formation rate equations. Nothing produced galaxies this massive this early. The gap between observation and theory was so large it stopped being a measurement error and started being a fundamental problem. What was driving this insane pace of growth? What force or condition existed in the early universe that has since been lost? Nobody knows yet, but sitting at the center of at least some of these impossibly large early galaxies was something even harder to explain. Stars do not form instantly. A star is born when a cloud of gas collapses under its own gravity. That collapse takes time. The gas has to cool. It has to condense. It has to spin down into a dense core hot enough to ignite nuclear fusion. In the modern universe, a star like our Sun takes roughly 10 million years to form from a collapsing cloud. Now multiply that by billions. The Milky Way today forms roughly 1 to 2 new stars per year. Building a galaxy of 100 billion stars at that rate takes roughly 100 billion years, longer than the current age of the universe. Obviously, galaxies found a faster way. Early in cosmic history, star formation rates were much higher. Conditions were different. Gas was denser. Temperatures were different. The process was more efficient. But Webb found galaxies where star formation rates were running at levels that broke even those elevated early universe estimates. Some of the ancient galaxies Webb detected were producing stars at a rate of over 1,000 solar masses per year. A solar mass is the mass of our Sunday. These galaxies were not making 1 or 2 new suns annually. They were generating the equivalent of 1,000 suns worth of new star material every single year. Sustained over millions of years, that pace builds up a very large galaxy very quickly. Here is a way to picture it. Imagine a city growing at normal speed, maybe a few hundred new buildings per decade. That is the modern Milky Way. Now imagine a city where 10,000 buildings go up every week. The skyline transforms in a fraction of the time. That is what Webb was watching happen in the early universe. But speed is only part of the problem. The efficiency is even harder to explain. In normal galaxy formation, a lot of the gas never makes it into stars. Radiation from newly formed stars blows surrounding gas clouds apart. Supermassive black holes at galaxy centers release enormous jets of energy that heat the surrounding gas and shut down further star formation. These are self-regulating mechanisms. They act as brakes on the process. Webb's early galaxies seem to be running without brakes. The efficiency with which they converted gas into stars was higher than any model predicted. Some teams estimated conversion efficiencies that would require nearly all available gas to be turning into stars, leaving almost no waste. In the real universe, that kind of efficiency should not be possible. One theory gaining traction is that the very first stars, known as population 3 stars, were massive beyond anything we see today. Some models predict they could have been hundreds of times the mass of the Sunday. They would have burned bright, lived fast, and died in explosions so powerful they seeded enormous amounts of material into their surrounding clouds, triggering rapid secondary star formation in a chain reaction. These titans would explain the acceleration. But nobody has directly observed a population 3 star yet. They may have all died before we could ever see one. And alongside these rapid-fire stellar explosions, something else was growing at the same impossible pace. Something darker and far more difficult to explain. Imagine a chain of 20 galaxies, connected end to end, stretching across space in a long, curved arc. Each galaxy in the chain is enormous by modern standards. Together, they span a distance of over 13 million light-years. That is so large, it makes the entire local group, the cluster of galaxies that includes the Milky Way and Andromeda, look like a small neighborhood. This structure is called the cosmic vine. Webb spotted it sitting in a region of sky known as the extended growth strip, and its existence breaks the timeline of the universe as we understood it. The cosmic vine was already fully formed when the universe was about 2 billion years old. On cosmic scales, that is incredibly young. The standard model of galaxy formation says that large-scale structures, like filaments and chains of galaxies, take many billions of years to assemble. Gravity works slowly over vast distances. Galaxies drift, interact, and gradually organize into the web-like pattern we see in the modern universe. Building something the size of the cosmic vine should have taken far longer than 2 billion years. Yet there it sits. Astronomers studying it found something even stranger than its size. The galaxies inside the vine are connected. They are not just neighbors by coincidence. They are feeding off the same stream of material, drawing gas along the dark matter filament that ties them together. They are growing in sync, building mass simultaneously, linked by invisible structure. Picture a string of beads. Each bead is a galaxy. The string between them is a thread of dark matter, something you cannot see but can only detect by its gravitational effect. The gas flows along the string from bead to bead, feeding star formation in each one. Now, picture that string curving across 13 million light-years of space. That is what the cosmic vine appears to be. This kind of connected large-scale structure is called a cosmic filament. The universe on its largest scales is organized into a web of filaments, sheets, and voids. Astronomers expected this web to exist, but they predicted it would take billions of years to form clear, massive filaments. The cosmic vine shows it happening far faster and far more dramatically than any simulation allowed. The vine also tells us something about where matter goes in the early universe. Galaxies growing along a filament are not random. They are being fed by the dark matter skeleton beneath them. The structure of the invisible universe is directing the visible one. Dark matter is not just a passive background. It is an active framework that channels matter into specific places at specific times. And here is where it gets weirder. The cosmic vine is a single structure in a single small patch of sky. Webb has found multiple such structures in different regions of its survey area. Each one is enormous. Each one formed earlier than models allow. Together, they suggest the large-scale organization of the universe was already well underway in its first 2 billion years. Something organized the universe faster than gravity alone can explain. And to understand what that something might be, you first have to look at the strange shapes these galaxies were leaving behind. Open any textbook on astronomy, and you will find galaxies sorted into familiar shapes. Spirals, like the Milky Way, with sweeping arms of stars curving out from a bright center. Ellipticals, round and smooth, like enormous cosmic eggs. Lenticulars, disc-shaped with no clear arms. These shapes dominate the modern universe, and astronomers assumed they dominated the early universe too, just younger and messier versions. Webb proved that assumption completely wrong. When researchers analyzed the shapes of galaxies in the early universe, they found something bizarre. More than half of them were elongated, stretched, long and flat and narrow. Astronomers started calling them prolate spheroids, but the description that stuck in the wider scientific community was simpler. They looked like surfboards, or pool noodles, or planks of wood drifting through the dark. These are galaxies that are far longer than they are wide. Some stretch several tens of thousands of light years in their long dimension, but are only a small fraction of that in width. They are oriented in specific directions relative to the surrounding cosmic environment, and they do not match any shape that standard galaxy formation models predict for the early universe. So why do they look like that? The answer points directly to the invisible structure of the universe. In the standard picture, galaxies form when gas and dark matter collapse into a rotating cloud. Rotation causes the gas to flatten into a disk. Stars form in that disk. The result is either a spiral or a flat elliptical. Rounded shapes come from spinning. But if the early universe had a very different kind of dark matter, the collapse would not flatten into a disk. Instead, it would stretch along the dark matter filament. The galaxy would grow along the grain of the invisible cosmic web beneath it, like a city that builds along a river valley rather than spreading out equally in all directions. These surfboard shapes, then, are direct imprints of the dark matter scaffolding. Each elongated galaxy is essentially a fossil trace of the filament it formed inside. By measuring the shapes, astronomers can map the invisible skeleton that drove the formation. There is one more detail that makes this discovery even stranger. The surfboard galaxies are not random in their orientation. In specific regions of the sky, they point in the same direction, lined up, as if they all formed along the same invisible track, like beads on a very long wire. When multiple galaxies in the same region all point the same way, it reveals the direction of the underlying filament. And when Webb started mapping those directions across large areas of sky, a pattern emerged. The dark matter web had a specific orientation in the early universe, a preferred direction that shaped everything growing inside it. The shape of a galaxy you could never see told the story of something enormous you cannot see at all. And that brings us directly to the thing at the heart of all of this. The thing no one can detect, no one can touch, and no one fully understands. You cannot see it. No telescope on Earth or in space can photograph it directly. Every instrument ever built passes through it without detecting a signal. And yet, it makes up roughly 85% of all the matter in the universe. Dark matter is the most abundant stuff that exists, and we have essentially no idea what it is. Here is what we do know. Gravity works on dark matter the same way it works on regular matter. Dark matter clumps together. It attracts other dark matter. It attracts regular matter. And over billions of years, it organized into a structure that looks, on the largest scales, like a three-dimensional spider web. Astronomers call this the cosmic web. The cosmic web has three basic features. Filaments are the long, thin strands, like threads in the web. Walls are where two filaments meet and form a flat sheet. Voids are the enormous empty spaces between filaments, huge dark regions where almost nothing exists. Galaxies form preferentially along filaments, and at the nodes where multiple filaments intersect. The biggest galaxy clusters in the universe sit at those intersection points, like knots in the web. This structure was predicted mathematically decades before it was confirmed. Surveys of the modern universe mapped millions of galaxies and found exactly this pattern. The web exists. It is real. But Webb gave scientists something no survey before it could provide: a view of the cosmic web in the early universe. In 2024, a team announced they had detected a cosmic filament that existed just 830 million years after the Big Bang. It was 3 million light-years long. That is longer than the distance between the Milky Way and the Andromeda galaxy. At that age, even finding a single mature galaxy was considered a major discovery. Finding an entire filament of cosmic web structure was something else entirely. This told scientists that the skeleton of the universe was already in place very early. The web was forming far faster than expected, and if the skeleton appeared early, the galaxies that grew along its threads would also appear early, and they would be shaped by the filament they formed inside. This is why the surfboard galaxies are so significant. They are pointing at the filaments that made them, and those filaments exist because of dark matter. But here is the part that gets seriously strange. The specific shapes of the early galaxies, the elongated surfboards, the clumping patterns, the smooth distribution of matter across filaments, do not quite match the predictions of standard dark matter models. Standard cold dark matter produces too much small-scale clumping. The observations from Webb are smoother, more stretched, more organized. Something about dark matter in the early universe behaves differently than the standard model expects. And there is one theory gaining serious attention that tries to explain it all. Every model in physics starts with assumptions. The standard model of cosmology assumes that dark matter is cold. Cold does not mean temperature. Exactly. It means slow. Cold dark matter particles move slowly relative to the speed of light and clump together on all scales, from the very small to the very large. That assumption has worked well for the large-scale structure of the universe. The overall cosmic web pattern matches cold dark matter predictions reasonably well, but when you zoom in on the details, especially in the early universe, problems appear. Too much small-scale clumping, galaxy shapes that do not fit, formation timelines that run ahead of schedule. A competing theory has been quietly gaining momentum. It goes by several names: fuzzy dark matter, ultralight dark matter, wave dark matter. The idea is that dark matter particles are not just slow, they are extraordinarily light, almost massless. And because of quantum mechanics, particles that light do not behave like particles at all. They behave like waves. Quantum mechanics tells us that all particles have a wave nature. For normal particles, that wave is so tiny, it does not matter at everyday scales. But for an ultralight particle, the quantum wave can extend across vast distances measured in thousands of light years. This means the dark matter does not clump at small scales. The wave nature of the particle prevents it. Instead, it spreads smoothly and creates structure only at larger scales. The result is a universe that looks like a cosmic ocean. The dark matter forms long, smooth, flowing structures with a specific wavelength determined by the particle's mass. Filaments appear not as tangled, dense threads, but as extended, smooth waves of density stretching across the early universe. When researchers fed Webb's data into simulations using wave dark matter rather than cold dark matter, something remarkable happened. The elongated galaxy shapes started matching. The smooth filaments appeared. The early formation timelines became more plausible. The simulations got closer to what Webb actually observed. This does not prove wave dark matter is real, but it suggests cold dark matter alone cannot explain the early universe as Webb sees it. The catch is enormous. Wave dark matter requires a particle called an ultralight axion. Axions are hypothetical. Physicists have proposed them to solve problems in particle physics, and some experiments are searching for them, but nobody has ever detected one. The particle has a mass so small it makes the electron look like a boulder. Building a detector sensitive enough to find it is a frontier challenge in experimental physics. So, we have a situation where the best available theory to explain Webb's galaxy shapes requires a particle that may or may not exist, and that we cannot yet directly detect. And while the debate about dark matter's true nature continues, there is a second crisis building in Webb's data. One that involves not the stuff that makes galaxies but the monsters that live at their centers. A black hole, 9 million times the mass of our Sun, was already fully formed just 570 million years after the Big Bang. Read that sentence again. 570 million years sounds like a long time, but the universe is 13.8 billion years old. At 570 million years, it was a toddler. And yet sitting at the center of an early galaxy was a black hole with a mass so extreme it would rank among the largest black holes in the modern universe. The problem is not that the black hole exists. Black holes form when massive stars collapse and die. The problem is the size. Getting a black hole to 9 million solar masses requires feeding it enormous amounts of material over a very long time. The fastest a black hole can grow is limited by the same Eddington rate that limits star formation. Radiation pressure from the infalling material eventually pushes more material away, slowing the feeding. Even growing at the maximum possible rate from the very beginning of time, a black hole starting from a single stellar collapse cannot reach 9 million solar masses in 570 million years. The math simply does not work. This is called the early black hole problem, and Webb has found dozens of examples of it. Some of these black holes are so large they have been nicknamed impossible objects by astronomers half-joking at conferences. The irony is that the telescopes before Webb could barely detect these early monsters. Webb sees them clearly, and seeing them clearly makes the problem impossible to ignore. How do you grow something that massive that fast? Several ideas exist. One possibility is that black holes in the early universe started bigger. Instead of beginning as stellar remnants, a few solar masses at most, some early black holes may have formed from the direct collapse of enormous gas clouds, skipping the star phase entirely. A cloud of gas, 100,000 times the mass of the Sun, collapses directly into a black hole. It starts big, and from that larger starting point, it can grow to 9 million solar masses within the available time. Another idea suggests that early black holes were feeding faster than the Eddington limit normally allows. If feeding bursts were brief and intense, rapid episodes of supercritical accretion separated by quieter periods. The average growth rate could exceed what steady-state models allow. A third theory involves mergers. If two or more smaller early black holes merged repeatedly and quickly, a single massive object could result without requiring any single one of them to have grown impossibly fast on its own. Each of these ideas has supporting evidence. None of them is fully confirmed, and the data from Webb keeps adding new examples that make the problem harder to dismiss. Black holes this big, this early, change the galaxies around them. Their energy poured out into the surrounding gas. And that brings us to a mystery that wraps around all of these discoveries like a fog. For most of cosmic history, black holes follow a predictable path. A massive star burns through its fuel. Gravity wins. The core collapses in milliseconds and forms a black hole with a mass of a few times that of the Sunday. Then it grows slowly by pulling in gas and, occasionally, merging with other black holes. Building up to millions or billions of solar masses takes an enormous amount of time and feeding, but some theorists believe the early universe offered a shortcut, a way to build a massive black hole without going through the star phase at all. The idea is called direct collapse. Here is how it works. In the very early universe, some regions contained enormous, pristine clouds of hydrogen and helium gas. These clouds had not yet been seeded with heavy elements by exploding stars, which means they could not cool efficiently. In the modern universe, gas clouds cool down and fragment. Small dense pieces break off and become individual stars. But without the right mix of elements to radiate heat away, a primordial gas cloud stays hot, and hot gas resists fragmentation. Instead of breaking into 100,000 small clumps that each become a star, the entire cloud collapses as a single unit, all the mass concentrated into one falling structure. The result is a single, extraordinarily dense object called a quasi-star. A quasi-star has a black hole growing at its center even while nuclear reactions burn in its outer layers. Eventually, the outer layers are consumed. What remains is a black hole that began its life already holding the mass of tens of thousands of suns. From that starting point, growing to 9 million solar masses in the available time becomes much more plausible. Webb has found candidates for these direct collapse black holes. A handful of objects in the early universe have properties that do not match normal black hole formation. Their host galaxies are unusually simple in chemistry, exactly what you would expect from pristine gas that never went through normal star formation. Their black holes are disproportionately massive compared to the galaxies they live in, another sign of a rapid shortcut in the formation process. The evidence is indirect. Nobody has watched a direct collapse happen. Simulating it requires computing power that can only now barely replicate the physics involved. But every new, early, massive black hole Webb finds adds to the pressure on theories that rely only on standard stellar collapse. The universe needed a fast track to build these monsters. Direct collapse is the leading candidate for what that fast track looked like. And those early black holes did not sit quietly. They sent energy pouring through the universe around them, energy that interacted with something filling all of early space, a dense, opaque fog that wrapped around everything. 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons and form hydrogen atoms. Before that moment, light could not travel. Everything was too hot, too dense, too tangled. Photons bounced off free electrons constantly and went nowhere. The universe was essentially opaque, an impenetrable fog of plasma. When hydrogen formed, the fog lifted for a short time. Light could travel. The universe became transparent. And the light from that exact moment is still visible today as the cosmic microwave background, a faint glow of ancient radiation coming from every direction in the sky. But then the fog came back as the first gas clouds collapsed and the very first stars began to ignite. The universe was filled with neutral hydrogen. Neutral hydrogen is extremely good at absorbing ultraviolet light. The light from the first stars had to pass through enormous walls of this gas. Most of it got absorbed. The universe went opaque again in a different way. Astronomers call this the cosmic dark ages, the period after the first stars formed, but before their radiation had cleared enough space to make the universe transparent again. Getting out of the dark ages required something called reionization. The ultraviolet radiation from early stars and from the growing black holes at galaxy centers had to ionize the surrounding hydrogen, stripping the electrons off again and making the gas transparent to light. This process took hundreds of millions of years and finished somewhere around 1 billion years after the Big Bang. But Webb found galaxies at redshifts corresponding to deep inside this fog. Light coming from 500 million, 300 million, even less than 300 million years after the Big Bang. For that light to reach us, it had to punch through the neutral hydrogen fog. Some of it did. And the fact that it did tells us the fog was thinner or more porous in those regions than models predict. Something was clearing the fog earlier than expected in some areas. The reionization process was patchy, uneven. Some regions cleared early, others stayed foggy longer. And the thing doing the clearing was the ultraviolet radiation pouring out of early galaxies and their central black holes. Webb is measuring exactly how much of that radiation escaped from early galaxies into the surrounding space. The answer determines how quickly different regions of the universe transitioned from opaque to transparent. And the measurements are revealing that some early galaxies were far better at leaking radiation than models predicted, while others held it in almost entirely. One specific galaxy Webb studied seemed to be punching a clear channel through the fog around it in a way that was extraordinary, even among early galaxies. Most early galaxies leaked a little ultraviolet radiation into the surrounding space, enough to slowly, patchily ionize the hydrogen fog over hundreds of millions of years. But Webb spotted something different. One galaxy in the early universe was doing something far more aggressive. It was blasting radiation out into the surrounding space with an efficiency that astronomers described as extreme. The fog around it was not just thinning, it was being carved open. The galaxy sits roughly 13 billion light-years away, placing it in the first billion years of cosmic history. Webb studied its light in detail and found a specific signature in the spectrum. Ionized helium inside the galaxy was being excited by radiation far more intense than any normal stars should produce. The energy output was consistent with an extremely active, fast-growing black hole at the galaxy's center, pouring ultraviolet and X-ray radiation into the surrounding gas. But the galaxy was also unusually compact. Its stars were packed tightly together in a very small region, far denser than typical galaxies at that era. Dense star formation combined with an active central black hole created a radiation field so intense it ionized not just the gas inside the galaxy, but large volumes of the fog surrounding it for millions of light-years in every direction. Astronomers identified this galaxy as what they call a leaker, a galaxy where a high fraction of the ultraviolet photons produced inside actually escape into the surrounding space, rather than being absorbed by internal gas. Leakers are rare in the modern universe. In the early universe, they appear to have been far more common, and they were crucial to ending the Dark Ages. Webb's measurements of leakers are allowing scientists to build a detailed map of how reionization actually unfolded, which regions cleared first, which galaxies drove the clearing, how the process spread through the cosmic fog like windows breaking one by one in a frozen house. The picture that is emerging is that reionization was not a smooth, uniform process. It was driven by a small number of extremely active, extremely efficient galaxies, punching holes and those holes gradually overlapping until the entire universe was clear. Some regions finished reionizing hundreds of millions of years before others. This matters because it means the early universe was extremely uneven. Structure did not develop evenly across space. It developed in pockets, in hotspots, in places where matter happened to clump early and black holes happened to grow fast. The cosmic story is one of extreme contrasts, not smooth, gradual development. And at the fringes of this patchy, fog-torn early universe, another class of object was showing up in Webb's data. Something nobody had a category for. Small, faint, and intensely red. They were everywhere, tiny, faint. But when Webb looked at them closely, unmistakably there, hundreds of small, compact objects scattered across the deep field images of the early universe. Their light had a distinctive quality, red, intensely red, far redder than any known class of galaxy or object at those distances should appear. Astronomers started calling them little red dots. At first, the assumption was simple. Red objects in the early universe usually mean one of two things. Either the object is so far away that the expansion of the universe has stretched its light toward red wavelengths, or the object contains a lot of dust, which absorbs short wavelength light and lets only longer, redder wavelengths pass through. Both are common and expected, but the little red dots did not fit neatly into either category. Their spectra, the breakdown of their light by wavelength, showed signatures of extremely dense, fast-moving gas. The emission lines in their spectra were broad, a signature astronomers associate with gas swirling at enormous speeds around a supermassive black hole. Some spectra showed signs of stellar populations, suggesting a galaxy was present. Others showed mostly black hole signatures. The objects appeared to be a mix of something, part growing galaxy, part extremely active black hole, and something about the combination was producing an unusual red color that did not match known templates. What made the situation more urgent was the number. Standard models predicted very few active black holes at these distances with these properties. Webb found hundreds, maybe thousands across the full sky. Whatever the little red dots are, they are common. They were a major feature of the early universe that every model before Webb had completely missed. Multiple teams have been studying them since Webb's first deep field images came in. Several papers have proposed explanations. Dense, dusty gas cocoons around growing black holes. Compact starburst galaxies forming stars so fast the dust generated by dying stars immediately clouds the emission. Unusual population of stars at very high temperatures. Each explanation accounts for some features but struggles with others. None of the explanations fully works. And then, inside the little red dots, one object stood out as different from the rest. One whose light signature was so extreme, so impossible to fit into any existing framework, that astronomers had to sit down and invent a completely new type of object to explain it. Among hundreds of little red dots, one stopped scientists cold. It sits roughly 12 billion light-years away, meaning its light left before the Earth existed. Webb spotted it in a region of sky called the Ultra-Deep Survey Field. When astronomers looked at its spectrum, the readout showed something so unusual they initially thought it was an instrument error. The object is now called the cliff. In the spectrum of this object, there is a feature called a Balmer break. A Balmer break is a sudden drop-off in the brightness of light at a specific wavelength, caused by hydrogen absorbing certain photons. In normal galaxies, a Balmer break is a moderate feature. It tells you something about the age and temperature of the stellar population. The cliff's Balmer break is extreme. It is so steep, such a sharp and massive drop in brightness at that wavelength, that it falls off the chart compared to any known galaxy. The break implies a hydrogen layer so thick, so dense, and so cold that it is absorbing an astonishing fraction of the light trying to pass through it. Standard galaxy models cannot produce a Balmer break that strong. No known combination of stars, gas, and dust generates a feature like this. Teams ran through every option, every stellar population model, every type of interstellar medium. Nothing produced the cliff's signature. Eventually, a team proposed a radical solution. Maybe the cliff contains a supermassive black hole at its center, a massive one, growing fast. And around that black hole, a sphere of extremely dense hydrogen gas has built up, far denser than any normal galactic gas cloud. This gas is thick enough to absorb almost all the light passing through it, creating the extreme Balmer break. But from the outside, the whole system glows brilliantly in infrared, because the absorbed energy has to go somewhere and it re-radiates in heat. The object looks like a galaxy from a distance, but inside, it is a black hole wrapped in a shell of gas so thick it acts as its own atmosphere. This proposed structure had never been considered before. Scientists needed a new term for it. A star has a nuclear furnace at its center. Gas surrounds it. The energy from the core pushes outward, and gravity pulls inward, and the balance between those two forces is what keeps a star alive and glowing. Now imagine the same structure, but at a scale billions of times larger. At the center, instead of nuclear fusion, there is a supermassive black hole consuming gas at an enormous rate. The energy released by matter falling into the black hole floods outward through the surrounding gas. That gas, a thick sphere of hydrogen around the entire system, absorbs the energy and glows. From outside, the whole object shines brightly in infrared. This is the proposed structure called a black hole star. It is not a star in the traditional sense. And it is not simply an active black hole nucleus either. It is a hybrid system where a growing black hole is encased inside a dense hydrogen atmosphere, held together by gravity, glowing as a unified object. The concept was already theorized years before Webb launched. Theoretical physicists had proposed that in the very early universe, when gas was pristine and abundant and had not yet been seeded with heavy elements by dying stars, conditions could allow a massive gas cloud to form around a growing black hole in a stable configuration. The cloud would be cool enough and dense enough to stay bound, and the energy from the black hole would keep it glowing. The cliff appears to be the first observational candidate for a real black hole star. Its extreme Balmer break fits a thick hydrogen shell. Its infrared brightness fits the energy output of a fast-growing black hole underneath, and its compactness fits the tight gravitational balance such a system would require. If the cliff is really a black hole star, it opens an entirely new category of cosmic object, and it suggests that during the first billion years of the universe, growing black holes may have spent a phase of their lives cocooned inside these shells, building mass rapidly before eventually burning through the surrounding gas and appearing as the luminous quasars and active galaxies we observe later. The little red dots might all be black hole stars, hundreds of them, scattered across the early universe. Each one a black hole wrapped in a hydrogen shell, glowing in infrared. Each one invisible to older telescopes that could not see well in that wavelength. And Webb, with its infrared vision tuned precisely to that wavelength, has been finding them everywhere it looks. A brand new type of object, in enormous numbers, and every model of the early universe completely missed them. There is something deeply unsettling about that. And the unease grows when you learn that even the expansion of the universe itself is not behaving the way science said it should. The universe is expanding. Everything in it is moving away from everything else. The rate of that expansion has a number, a measure of how fast space itself is stretching, called the Hubble constant. For decades, cosmologists have tried to pin down that number precisely. There are two main ways to measure it. Both should give the same answer. The first method looks at the distant past. Scientists study the cosmic microwave background, the ancient glow of light left over from when the universe was only 380,000 years old. The pattern of temperature variations in that glow encodes information about the physics of the early universe. From that data, scientists can calculate how fast the universe should be expanding today. Teams using this method consistently get a number around 44 miles per second per megaparsec. A megaparsec is a unit astronomers use for very large distances, roughly 3.3 million light-years. So the number means that for every 3.3 million light-years of distance between two objects, those objects are moving apart at 44 miles per second. The second method looks at the present-day universe. Scientists measure distances to nearby galaxies using specific types of exploding stars called Type 1a supernovas. These explosions always release the same amount of energy. so their apparent brightness tells you exactly how far away they are. Combining distance measurements with the observed velocities of galaxies gives a direct measurement of the expansion rate today. Teams using this method consistently get a higher number, around 47 miles per second per megaparsec. Two different methods, two consistent results within each method, but the two methods disagree with each other, and the disagreement is too large to be a measurement error. This gap is called the Hubble tension. For years, some scientists suspected it might go away once measurements got precise enough. Webb was supposed to help resolve it. Instead, Webb made the tension worse by making both measurements sharper and confirming that neither one is wrong. Both measurements are right, and they disagree. That means something real is causing the discrepancy, a physical process happening in the universe that the standard model does not account for. Something is making the present-day universe expand faster than the early universe physics predicts it should. What is that something? Scientists do not know. The leading candidates include a form of dark energy that changes strength over time, an additional type of radiation present in the early universe that slightly altered the timing of structure formation, or a modification to the theory of gravity itself at very large scales. Whatever it is real, and it is not small. A gap of 3 miles per second per megaparsec between the two measurements sounds minor, but it compounds across the full scale of the observable universe into something enormous. The universe is measurably, consistently, expanding faster than our best physics says it should. Something is out there, pushing, and nobody has found it yet. The universe is accelerating, not just expanding, accelerating. The galaxies rushing away from us are not slowing down over time, pulled back by gravity the way you would expect. They are speeding up. Something is pushing them apart faster and faster with every passing billion years. Scientists already had a name for this before Webb launched: dark energy. It was discovered in 1998 when two independent teams measuring distant supernovas both found the same shocking result. The expansion of the universe was not decelerating, it was accelerating. Both teams won the Nobel Prize for the discovery, and dark energy became the name given to whatever was causing it. In the standard model, dark energy is described as a cosmological constant, a fixed, unchanging energy density built into the fabric of space itself. Every cubic inch of empty space contains the same amount of dark energy, everywhere, at all times. As the universe expands, more empty space is created, and more dark energy comes with it. That extra energy keeps pushing the expansion faster. This model worked. It fit the data. It became a pillar of the standard cosmological model. But the Hubble tension is now suggesting that dark energy is not constant, because if it were constant, both methods of measuring the expansion rate should agree. They do not. The universe today is expanding faster than the early universe physics, combined with a constant dark energy, predicts. The only way both measurements can be right simultaneously is if dark energy changed over time, weaker in the early universe, stronger today, or possibly something shifted in the late universe that added extra acceleration. One emerging theory proposes that dark energy is not actually a fixed constant, but a dynamic field that evolves. Physicists call this quintessence, a slowly rolling field that was weaker in the past and has been growing in strength over time. As it strengthens, it pushes the expansion harder. That could explain why today's measured expansion rate is higher than what the early universe predicts. Another theory proposes that there is a new form of energy, called early dark energy, that briefly appeared and then faded in the first moments of the universe. Its presence would have slightly compressed the timing of early structure formation, shifting the predictions for what the expansion rate should be today. Some simulations using early dark energy models reduce the Hubble tension significantly. A third possibility is more radical. Gravity itself may work differently at very large scales than general relativity describes. Modified gravity theories have been around for decades but have always been hard to confirm. If gravity's behavior changes at the scale of the entire observable universe, every model built on standard gravity would need revision. Webb cannot directly identify which of these is correct, but it is ruling out explanations one by sharpening the measurements on both sides of the tension. Every time a new Webb data release comes out, the gap between the two expansion rates holds. The unknown force does not go away when you look at it more carefully. It gets clearer. Something is driving the universe apart at a rate that no confirmed physics explains. And the strangest part is not that we cannot identify it. The strangest part is that it makes up roughly 68% of everything that exists. The universe is mostly made of something we cannot explain, and the crisis that represents is only getting harder to avoid. Webb was not built to look at single objects. It was built to map entire regions of the sky in extraordinary detail. And in 2023, a massive observing campaign called the Cosmos Webb Survey began doing exactly that. The survey targeted a patch of sky in the constellation Sextans. It accumulated hundreds of hours of Webb observation time over multiple months. The resulting dataset covered a region large enough to contain roughly 54,000 galaxies visible to Webb's instruments. And buried inside that enormous collection of galaxies, the survey team found something that changed the scale of Webb's discoveries. Roughly 1,700 galaxy groups. A galaxy group is a gravitationally bound collection of galaxies, anywhere from a few members to dozens. The Milky Way sits in one called the local group, which contains about 80 galaxies. These groups are the building blocks of the large-scale structure of the universe. Clusters form when groups merge. Superclusters form when clusters gather. The entire cosmic web is built from these nested, gravity-bound collections. The Cosmos Webb Survey found over 1,700 of them from an era when the universe was just 1 billion years old. At that age, the standard model predicted a much smaller number of organized groups. Groups that large and that numerous require time to form. Gravity needs to work over many millions of years to pull galaxies into stable, bound systems. 1 billion years into cosmic history was considered too early for this level of organization. The survey found otherwise. The galaxy groups in the Cosmos Webb data were not randomly scattered either. They were arranged, connected by filaments of matter stretching between them. Some were already beginning to merge into larger structures. Some showed clear signs of sharing a common gas reservoir, feeding off the same dark matter filament running beneath them. The team built a three-dimensional map from the data. When rendered visually, it looks like a foam of bubbles, with galaxy groups sitting at the intersections of bubble walls and enormous voids occupying the empty interiors. The cosmic web, in miniature, 1 billion years after the Big Bang. What the map revealed is that the universe organized itself into this web-like pattern far earlier than any model produced before Webb. The structures were already in place at 1 billion years, which means the process that created them began even earlier, which means the seeding of structure formation happened in the first few 100 million years, right when the improbably large early galaxies were already forming. Everything connects. The early giant galaxies, the fast black holes, the cosmic vine, the surfboard shapes, the filaments, the galaxy groups. They are all part of the same story. The universe built its large-scale structure faster than any model allowed. And that large-scale structure did not always grow quietly. Galaxies are not peaceful objects. In the modern universe, galaxy collisions happen on timescales of hundreds of millions of years. Two galaxies drift toward each other over billions of years, distorting each other gravitationally, exchanging stars, triggering waves of star formation, and eventually merging into a single larger system. The process is slow by human standards, dramatic by cosmic ones. In the early universe, collisions were more frequent. Galaxies were packed into smaller volumes of space. The cosmic web was still assembling. Galaxies that formed near each other along the same filament were moving toward each other, and the distances between them were shorter than they would become as the universe expanded. Webb captured this violence in extraordinary detail in a system known as Webb's Quintet. This is a group of 5 galaxies. 4 of them are locked in a slow, grinding gravitational interaction about 290 million light-years away. The 5th is a foreground galaxy, physically unrelated, sitting in the same line of sight. Webb's image of this system showed what no previous telescope could reveal: the shock waves running through the gas between the colliding galaxies. When galaxies collide, they do not collide the way 2 solid objects would. Most of a galaxy is empty space. Stars pass through each other's galaxy without hitting anything. What does collide is the gas. Enormous clouds of hydrogen and helium, moving at hundreds of miles per second, slam into each other and generate shock waves. Those shocks heat the gas to temperatures of tens of millions of degrees. Webb saw that hot gas glowing in infrared, tracing the exact paths of the collisions. One of the galaxies in the group is being shredded. Its outer regions are pulled into long tidal tails, stretching across hundreds of thousands of light-years. Knots of compressed gas along those tails are igniting new bursts of star formation. The collision is destroying one structure while creating another. In the early universe, Webb found systems where this process was happening to many galaxies at once, in tight, dense clusters. Multiple objects colliding simultaneously, exchanging gas, triggering starbursts, feeding central black holes with gas compressed by the collision, and reshaping their entire surrounding environments. These collisions help explain some of the rapid growth seen in early galaxies. A merger brings 2 gas reservoirs together into one. The shock of collision compresses gas clouds and triggers rapid star formation. Central black holes of merging galaxies eventually merge themselves, producing the massive early black holes Webb keeps finding. Galaxy collisions in the early universe were engines. They drove the rapid assembly of mass and structure that the standard model says happened too slowly. And Webb did not just watch this violence from a distance. It used a trick of the universe itself to zoom in closer than any instrument should be able to reach. Einstein's general relativity makes a prediction. Mass warps space. Light follows the curves in space. So light passing near a massive object gets bent. This is not a metaphor. It is a physical effect that has been measured and confirmed for over a century. The first confirmation came in 1919, when scientists measured the position of stars near the Sun during a total solar eclipse and found they appeared slightly shifted from their normal positions. The Sun's mass was bending the starlight as it passed by. Scaled up to the mass of an entire galaxy cluster, this effect becomes extraordinary. When Webb looks at a distant galaxy cluster sitting between us and an even more distant object, the cluster's mass acts like a lens. It bends the light from the object behind it, magnifying and distorting it. Depending on the geometry, that distant background object can appear as a smeared arc, a series of multiple images, or a perfect glowing ring. In 2023, Webb captured a gravitational lens so precise it created a nearly complete ring of light around a foreground galaxy cluster. The background object was a quasar, an extremely luminous galaxy with an active black hole at its center, sitting roughly 11 billion light-years away. The cluster in front of it, sitting about 6 billion light-years away, bent the quasar's light into a bright, nearly circular ring floating in the dark. Researchers called it the cosmic jewel or the jeweled ring. The ring is beautiful, but its scientific value goes beyond appearance. The shape and brightness of the ring tells astronomers exactly how much mass the foreground cluster contains, including the invisible dark matter component. By modeling the lens geometry precisely, Webb can weigh the dark matter in the cluster with an accuracy no direct observation could achieve. In one observation, Webb found something even more extreme. Looking through a cluster called the Dragon Arc cluster, Webb spotted a distorted, stretched spiral galaxy behind it. The magnification from the cluster was so strong that individual stars inside the background galaxy became visible, 44 of them. scattered across the galaxy's arms, each one a single star billions of light years away. Seeing individual stars in another galaxy across 6.5 billion light years is an achievement that should not be possible without gravitational lensing. The cluster's mass turned the surrounding space into a natural telescope, adding a magnification layer that Webb's own mirrors alone could not provide. And that magnified view revealed details about star formation, stellar populations, and galactic structure in the early universe that would otherwise be permanently out of reach. The universe itself handed Webb a tool to see further than it was designed to see. The galaxy had been seen before. Hubble had detected it years earlier as a smeared, distorted arc in the background of its foreground cluster. Interesting, but unresolvable. Just a curved smudge with some color information and a rough distance estimate. Not enough detail to tell you much. Webb changed that completely. When Webb turned its infrared instruments on the Dragon Arc, the smear became a gallery. The gravitational lens was stretching and brightening the background galaxy so dramatically that Webb could resolve individual features inside it. And among those features, sitting along the bright lensed arcs, were 44 points of light that resolved cleanly as individual stars. These stars are roughly 6.5 billion light-years away. The light arriving at Webb's mirror left them before the solar system formed, and yet Webb can see them as separate points, distinguish their colors, estimate their temperatures, and classify their types. The stars themselves were remarkable. Several were far more luminous than anything in the Milky Way, members of a class called luminous blue variables, enormous stars burning at temperatures and brightnesses that pushed the limits of stellar physics. Some appeared to be in binary systems, 2 stars locked in close orbit. One appeared to be in a flaring state, brightening temporarily due to an instability in its outer layers. The galaxy they live in was actively forming stars at the time its light was emitted. The lensed image showed regions of intense star formation clustered along the galaxy's spiral arms. Hot, young, massive stars glowed blue in certain bands of infrared light. Older, cooler, stellar populations showed up in redder wavelengths. Webb's ability to observe across multiple infrared wavelengths simultaneously allowed the team to map different populations of stars across the galaxy's face in a single observation. What scientists learned from the Dragon Arc extended beyond the single galaxy. By comparing the stellar populations they saw at 6.5 billion light-years with populations observed in more modern galaxies, they could track how star formation rates and stellar compositions changed over the last 6 billion years of cosmic history. The individual stars in the arc became data points in a much larger story about galactic evolution. The Dragon Arc also served as a calibration check for gravitational lensing models. By resolving individual stars and comparing their positions in different lensed images, the team could refine their model of how the foreground cluster's mass was distributed, including how the dark matter was arranged inside it. Each individual star was a clue. Together, 44 clues about a galaxy, its history, and the invisible mass bending its light into our line of sight. And gravitational lensing created another image so striking it looked less like science and more like something out of a dream. 11 billion light-years away, a quasar blazes. A quasar is a galaxy whose central black hole is consuming gas so rapidly that the energy released outshines the combined light of every star in the galaxy around it. Some quasars emit more energy in a single second than our Sun will release in its entire lifetime. They are the brightest sustained sources of light in the universe. Between us and this quasar, at roughly 6 billion light-years away, sits a galaxy cluster, massive, dense. Its combined gravity, including the gravity of the dark matter surrounding it, amounts to hundreds of trillions of times the mass of our Sunday. That mass bends space around it, and the light from the quasar, traveling through that curved space, gets bent into a circle. Webb captured this alignment in a single image, a nearly perfect ring of bright light curving around the foreground cluster, evenly bright, nearly symmetric, a circle drawn in ancient quasar light, bent around a gravitational lens by the geometry of warped space. Scientists immediately recognized it as an Einstein ring, the theoretical perfect alignment that Einstein himself calculated was possible, but considered too rare to ever observe cleanly. Webb found one sharp enough to use for precise measurements. The ring tells scientists two separate things simultaneously. The first thing is about the quasar. Because the lens magnifies the background source, Webb can study the quasar in more detail than its distance would normally allow. The spectra of the ring's light carry information about the quasar's black hole mass, accretion rate, and the chemical composition of gas falling into it. All of this from 11 billion light-years away. The second thing is about the lens, the exact shape of the ring, where it is thickest, where it is brightest, whether it closes perfectly or shows slight asymmetry, reveals the mass distribution of the foreground cluster with extraordinary precision, including the dark matter. A perfect Einstein ring is a near-perfect weighing tool for invisible mass. The measurements from this ring gave the most precise mapping yet achieved of dark matter in a galaxy cluster. The dark matter did not follow the visible galaxies exactly. It formed a smoother, more extended halo around the cluster, concentrated at the center, but trailing off in a specific profile that matched the predictions of certain dark matter models better than others. One observation, two separate scientific prizes, and a reminder that the universe's geometry has been bending light around its own structures for billions of years, waiting for a telescope sensitive enough to notice. But Webb did not just catch mature structures bending light. It reached further back and found the earliest star clusters ever seen forming. Objects so ancient they push right up against the edge of what light can carry to us. 460 million years after the Big Bang, something was already building organized clusters of stars. Webb found them inside a gravitationally lensed arc, a system astronomers named the Cosmic Gems Arc. The lensing from a foreground cluster magnified the background galaxy enough to show internal structure that would otherwise be completely invisible at that distance. And what Webb saw inside were 5 compact, intensely bright regions of star formation. Not individual stars, clusters, tight, dense balls of young stars forming together in pockets of gas that had already collapsed and ignited. Proto-globular clusters. Globular clusters are ancient, ball-shaped groups of stars held together by their mutual gravity. The Milky Way today has roughly 150 of them, orbiting its outer regions. They are among the oldest structures in any galaxy, relics of the earliest epochs of star formation. Astronomers have long suspected that globular clusters formed very early in cosmic history, but direct evidence has been hard to obtain because the objects are so distant and so small. The Cosmic Gems Arc gave Webb a lensed magnification strong enough to see these forming clusters directly at 460 million years after the Big Bang, making them the oldest protoglobular clusters ever observed. Each one is compact, only a few hundred light-years across, but packed with stars forming at an intense rate. Their combined brightness in the ultraviolet suggests the stars inside are very young and very hot, barely millions of years old. The discovery filled in a critical gap in galaxy formation theory. Globular clusters were not scattered randomly through early galaxies. They formed in specific, dense pockets where gas compression was highest. The Cosmic Gems Arc shows those pockets already active less than 500 million years into cosmic history. The host galaxy itself is remarkable. Despite its age, it already shows multiple distinct star-forming regions with different properties. Some regions are forming stars rapidly. Others have already slowed. The galaxy is not uniform. It has structure, variation, a complexity that speaks to a history of environmental differences, different gas densities, different radiation fields, different feedback from newly born stars. At 460 million years old, this galaxy had already developed an internal geography, and the chemistry inside some of these ancient objects revealed something that went one step further into the impossible. Heavy elements are not primordial. The Big Bang produced hydrogen and helium and tiny traces of lithium. That is essentially all. Every heavier element in the universe, every atom of carbon, oxygen, nitrogen, iron, silicon, every element that makes up planets, atmospheres, and living things, was forged inside stars and scattered into space when those stars died. A star spends its life fusing lighter elements into heavier ones in its core. When it dies in a supernova explosion, it blasts those heavy elements into the surrounding gas. The next generation of stars forms from that enriched gas, and the process repeats. Each generation adds more heavy elements to the supply. This recycling takes time, billions of years, according to standard stellar evolution models, to build up significant quantities of complex chemistry. Webb found a galaxy called JADE SGSZ 140 that existed just 290 million years after the Big Bang. When the team analyzed its spectrum, they found oxygen, clear, unmistakable oxygen emission lines, the chemical signature of an element that requires at least one full generation of stellar evolution to produce. At 290 million years, the universe was not supposed to have enough time for even one full stellar generation to complete at the massive scale required to enrich an entire galaxy with oxygen. Yet there it was. The oxygen abundance was not a trace amount either. It was substantial enough to significantly affect the galaxy's cooling rate and star formation process. This galaxy had already cycled through enough stellar generations to build a genuine chemical library. Carbon was present. Nitrogen signatures appeared in follow-up observations. The galaxy was, chemically, already complex. This problem, called the chemical enrichment problem, sits alongside the mass problem and the size problem as one of the core crises Webb has created in cosmology. You cannot build complex chemistry without stellar generations. You cannot have stellar generations without time, and the time available simply does not match the chemistry observed. One possible explanation is that the very first stars were so massive, thousands of times the mass of the Sun, that they burned through their entire fuel supply in just a few million years rather than billions. A star that massive lives fast and dies explosively, scattering enormous quantities of heavy elements in a single supernova. A brief epoch of these titans could have enriched the early universe with surprisingly complex chemistry in a very short window of time. If that is correct, it means the universe's first chapter was driven by stellar giants that no longer exist anywhere today, and their legacy is chemistry that, by any normal accounting, arrived far too early. What allowed Webb to see any of this was a capability that no telescope before it possessed, one that changed what astronomers could detect and where they could look. Light comes in many flavors. Human eyes see a narrow slice of the full spectrum, the wavelengths we call visible light. Shorter wavelengths, like ultraviolet and X-rays, carry high energy but get blocked by Earth's atmosphere. Longer wavelengths, like infrared and radio waves, carry less energy but can pass through obstacles that block visible light. Dust is one of those obstacles. Cosmic dust, tiny solid particles of carbon and silicate scattered through galaxies and star-forming nebulae, is extremely effective at absorbing and scattering visible light. Many of the most active, most interesting regions of the universe are buried behind walls of dust that completely block the view from any visible light telescope. Infrared light passes through that dust. The longer wavelengths simply slide through the particles instead of being scattered by them. A telescope that sees in infrared can look straight through dust clouds that would be completely opaque to a visible light instrument. Webb was built to see in infrared. Its mirror, its detectors, and the entire design of its sunshield and cooling system were chosen to optimize infrared sensitivity. The result is a telescope that can see through dust anywhere in the universe. This superpower has two separate benefits. The first is that Webb can see into the interiors of star-forming regions here in our own galaxy and in nearby galaxies. Entire stellar nurseries that Hubble saw only as featureless, brown blobs of dust became transparent in Webb's infrared vision. Webb revealed dense knots of gas collapsing into protostars, jets of material firing out from newly forming star systems, and the complex, turbulent structure of star-forming clouds in extraordinary detail. The second benefit applies to the distant universe. Ancient light traveling toward us gets stretched by the expansion of the universe. Light that began its journey as visible or ultraviolet, the wavelengths emitted by hot young stars, arrives at Earth, shifted into infrared. The further away an object is, the more its light is stretched, and the longer the wavelength at which it arrives. Webb's infrared detectors are specifically tuned to catch light that left its source anywhere from a few 100 million years to over 13 billion years ago. Every deep field image Webb takes in infrared is simultaneously a look through cosmic dust and a look back through deep time. The two benefits combine in every single observation. Without infrared vision, the early universe would be essentially invisible. The light from its galaxies, stretched by expansion, arrives in a wavelength range that Hubble and other visible light telescopes could barely detect. Webb catches it cleanly. This is why every other discovery in Webb's catalogue was impossible before it launched. The telescope did not just improve on what came before, it opened a window that was previously shut. And when Webb used that window to revisit objects in our own cosmic neighborhood, familiar objects became completely new discoveries. 3,800 light-years from Earth, a star is dying. The Southern Ring Nebula is one of the most studied objects in the southern sky. Earlier telescopes photographed it for decades. It appears as a glowing oval of gas surrounding a faint central star. The leftover shell, ejected by a star that ran out of fuel and shed its outer layers in a gentle, expanding bubble. Beautiful, well understood. Or so scientists thought. Webb changed that. When Webb's infrared and near-infrared cameras captured the Southern Ring Nebula, they did not see what previous images showed. They saw multiple shells of gas layered around the central star, each one a separate ejection event from different points in the star's long death process. They were not visible in previous observations because dust between and within the shells blocked the optical light. In infrared, the dust became transparent, and every shell appeared clearly, one inside the other like the layers of an onion. There was also a second star. Sitting close to the central dying star was a companion, a fainter star whose gravitational influence had been shaping the ejected gas as it expanded outward. The two stars orbited each other, and their orbit introduced asymmetry and complexity into what had appeared to be a simple, symmetric shell. Earlier telescopes could barely distinguish the two stars. Webb resolved them clearly and showed how the companion was pulling the ejected material into spiral patterns that wrapped through the nebula. The chemistry revealed in Webb's spectra was also unexpected. The dying star was not just releasing hydrogen and helium. Its spectrum showed carbon compounds, molecules called polycyclic aromatic hydrocarbons, forming in the cooling outer shells of the ejected gas. These are organic molecules, the same type found in interstellar space and in the atmospheres of planets. They were forming spontaneously in the cooling gas of a dying star. This tells scientists something important about where the basic building blocks of chemistry come from. Dying stars are not just scattering heavy elements. They are actively assembling molecular structures in their final breath, sending complex chemistry into the interstellar medium, where it can eventually wind up in the gas clouds that form new stars and planets. The Southern Ring Nebula, which seemed fully understood, turned out to be a complex, layered, chemically rich system that only became visible once a telescope could see through the dust. And Webb's ability to see through barriers did not stop at dust clouds or galactic distances. It extended outward in unexpected directions too, including right here in our own solar system. Uranus is one of the most overlooked planets in the solar system. It sits nearly 2 billion miles from the Sunday. It rotates on its side, its axis tilted so far that its poles point almost directly at the Sun for part of its long orbit. Its surface is a uniform blue-green, with almost no visible features in most telescope images. When Voyager 2 flew past it in 1986, the flyby lasted only a few hours, and scientists were struck by how featureless and quiet it looked compared to Jupiter or Saturn. Webb showed that quiet was an illusion. In early 2026, a team studying Webb's infrared observations of Uranus published results that revealed something nobody had seen clearly before: glowing bands of auroral light shimmering over the planet's poles, and alongside the bright auroral regions, dark patches where magnetic activity was suppressing the emission of infrared radiation from the atmosphere below. Auroras are not new discoveries. Earth has them. Jupiter and Saturn have spectacular ones. They form when charged particles from the Sun or from a planet's own magnetosphere rain down along magnetic field lines and excite gases in the upper atmosphere. The excited gas glows. Uranus has a complicated magnetic field. Its axis is not aligned with its rotation axis the way Earth's roughly is. The magnetic pole wanders significantly across the planet's surface. This produces auroras in unusual places, at high latitudes, but in specific patches rather than the uniform polar rings seen at Earth or Jupiter. What Webb detected was auroral emission in the infrared, specifically from a molecule called the trihydrogen cation. This ion forms in the upper atmosphere when cosmic rays or charged particles ionize hydrogen gas, and it glows in the infrared when excited. Webb's instruments picked up this glow 3,106 miles above the cloud tops of Uranus, far higher in the atmosphere than any previous instrument had detected. The dark patches proved even more interesting. Regions of suppressed infrared emission adjacent to the bright auroras suggest local magnetic disturbances strong enough to alter how heat flows upward through the atmosphere. The planet's magnetic field is actively reshaping its atmospheric energy distribution in real time. Uranus turned out to have a dynamic, energetic upper atmosphere with complex magnetic interactions that previous instruments were simply not sensitive enough to detect. Webb found all of it in a single set of observations. The same instrument, revealing the edge of the observable universe, was simultaneously uncovering new physics in our own backyard. And when scientists used all of Webb's data together, not just the targeted observations but the full survey programs, they built something nobody had ever had before. In 2025, a team announced the completion of a survey that had consumed years of observation time across multiple space and ground-based telescopes, with Webb providing the deepest and most detailed portion. The result was a map of the universe, spanning over 13 billion years of cosmic history. The map covers a stretch of sky large enough to contain hundreds of millions of galaxies. It traces the positions of galaxies from the very nearby universe, where light has been traveling for only a few million years, all the way out to objects whose light left them over 13 billion years ago, when the universe was less than a billion years old. Within that span, the three-dimensional structure of the universe is laid out. The cosmic web is visible in the map, not inferred. Visible, long filaments of galaxies running for hundreds of millions of light years, flat sheets where filaments intersect, and enormous voids, regions of space hundreds of millions of light years across that contain almost nothing at all. One of the most striking features is how the voids have grown over time. In the early universe, the variations in galaxy density were smaller. The web existed but was less pronounced. Over billions of years, gravity has pulled matter away from the voids and concentrated it into the filaments and nodes. The voids have emptied further. The filaments have thickened. The contrast between the dense regions and the empty ones has increased dramatically. This process, called structure growth, can be measured directly from the map by comparing the density contrast at different epochs. And those measurements are another test of the standard model, because the standard model predicts exactly how fast structure growth should proceed given the known amounts of matter and dark energy. The measurements from the map do not quite agree with the predictions. Structure has grown slightly faster in certain epochs than the model allows. The discrepancy is smaller than the Hubble tension, but points in the same direction. Something in the universe is pushing structure to form and concentrate faster than standard physics predicts. This is yet another thread in the same knot. The early galaxies formed too fast. The Hubble tension shows expansion proceeding too fast. The cosmic web assembled too fast. The map confirms that structure growth itself ran ahead of schedule at certain points. All the arrows point toward the same conclusion. The standard model has something missing, some physics or some component of reality that it does not account for, and the map makes that conclusion harder to dismiss than any single observation could. The universe is trying to tell us something, and scientists are only beginning to read the message. The cosmic web is not a metaphor. It is a real physical structure, and Webb is giving scientists their best ever look at it in the early universe. Here is what it actually looks like. Imagine taking the entire observable universe, everything within 46 billion light-years of Earth, and compressing it into a model you could hold. At that scale, individual galaxies would be invisible. What you would see instead are the filaments, long, thin threads of matter and galaxies winding through space. They intersect at nodes where the largest clusters of galaxies sit. Between the filaments are the voids, vast empty spaces that dwarf anything else in the universe. A typical filament in the modern universe might run for hundreds of millions of light-years. It might be only a few million light-years wide. The contrast between the dense filament and the empty void around it is enormous. Hundreds of galaxies might be threaded along the filament. The void beside it might contain almost none. The voids are not perfectly empty. Occasional, small, isolated galaxies drift through them, pale exceptions to the general emptiness. And the voids are not still. They are slowly expanding. The matter inside them is raining outward, pulled toward the filaments by gravity. Over billions of years, the voids get emptier and the filaments get denser. Webb's observations of the cosmic web in the early universe reveal a younger, less extreme version of this structure. The filaments exist, but they are less defined. The voids are smaller, the density contrasts less dramatic. The universe, at 800 million years, looks like a rough sketch of the web it will eventually become. One of the most remarkable Webb results was the detection of a filament of ionized gas connecting two early galaxies separated by millions of light-years. The gas in the filament glowed faintly in a specific emission line called Lyman alpha, emitted by hydrogen gas that has been ionized by nearby radiation. Webb's sensitivity in this wavelength was high enough to detect the filament's glow, even though it is many times fainter than the galaxies at its ends. This kind of direct detection of interfilament gas is extremely rare. The gas is so diffuse and spread over such vast distances that it produces almost no signal. Finding it at all required Webb's full sensitivity and hundreds of hours of observation time. The result is a direct image of the skeleton of the universe. The dark matter scaffolding cannot be photographed, but the gas that flows along it, glowing faintly in the ultraviolet emission lines that Webb captures, gives its shape away. The web is visible if you know what light to look for, and that web, its presence confirmed earlier than any model predicted at scales larger than models allowed, brings together every crisis Webb has uncovered into a single picture of a universe that organized itself faster, more efficiently, and more dramatically than any theory prepared us to expect. The crisis this represents has a name. Add it all up: galaxies too massive, too early, black holes too large, too soon, chemistry too complex for the available time, a cosmic web already assembled when it should still be forming, the expansion rate of the universe disagreeing with itself, the structure growth running ahead of predictions. None of these problems existed before Webb launched. Or more precisely, hints of some of them existed, but they were small enough to attribute to measurement errors or sample biases. Webb made the hints into hard data. It pushed each discrepancy past the threshold where it can be waved away. Cosmologists have a phrase for when observations disagree with a theoretical prediction at a level of 5 sigma or greater. It means the chance of the disagreement being a statistical fluke is less than 1 in 3.5 million. Several of Webb's findings are approaching or exceeding that threshold. The standard model of cosmology, called lambda cold dark matter, rests on a few key ingredients: regular matter, dark energy, and the specific way gravity operates, as described by Einstein's general relativity. The model has been extraordinarily successful. It correctly predicted the large-scale structure of the modern universe. It correctly predicted the detailed pattern of temperature fluctuations in the cosmic microwave background. It correctly predicted the relative abundances of light elements from Big Bang nucleosynthesis. But it did not predict what Webb found. It cannot produce the observed galaxies at the observed ages with the observed masses using only the allowed ingredients. Running simulations with standard ingredients consistently produces a universe that is slower, smoother, and less organized at early times than what Webb observes. Physicists are now openly discussing whether lambda cold dark matter needs to be patched or replaced. Some argue the model just needs refinements, new details about how stars form and how black holes grow that can allow faster early development without breaking the larger framework. Others argue the problems run deeper, that the model's fundamental assumptions about dark matter, dark energy, or gravity itself are wrong at some level. The debate is real, active, and unresolved. Papers proposing modifications to the standard model are appearing weekly. Some gain traction, some are ruled out by the next batch of Webb data. The science is moving faster than at any point in the history of cosmology. What is clear is this: the universe Webb is showing us is more extreme, more active, and more organized at early times than anyone expected. That fact is no longer in question. The question is what physical reality underlies it, and the attempts to answer that question are pushing physics into territory it has never explored before. If the standard model of cosmology needs replacing, what comes next? Several serious contenders are being developed and tested. Each one is strange. Each one would, if confirmed, overturn something that has been considered settled science for decades. The first idea targets dark matter. Wave dark matter, the model where dark matter behaves like a quantum wave rather than a slow particle, produces smoother filaments and elongated galaxy shapes that better match Webb's observations. If wave dark matter is confirmed, it would require finding ultralight axion particles, objects so light that the most sensitive detectors ever built can barely constrain their properties. New experiments proposed for the next decade aim specifically at axion detection. If one succeeds, the structure of the early universe would be explained without touching any other part of the model. The second idea targets dark energy. Several independent analyses of galaxy survey data, including data from the Dark Energy Spectroscopic Instrument released in 2024, suggested that dark energy may not be constant. Its strength appears to have varied over the history of the universe. If dark energy is dynamic rather than fixed, every calculation about cosmic expansion would need revision. The nature of the dark energy field, whether it is a particle, a field, a property of space-time itself, remains completely unknown. The third idea is more radical. Some physicists propose modifying gravity. Einstein's general relativity has passed every test performed within the solar system and at the scale of individual galaxies. But at the scale of the full cosmic web, over distances of hundreds of millions of light-years, it has never been precisely tested. Modified gravity theories, which change how gravity behaves at very large scales or very low accelerations, can produce faster structure growth and altered expansion histories. These theories have a difficult track record, with most proposed modifications failing when tested against new data. But the field is active, and some versions remain plausible. The fourth idea involves the very first moments after the Big Bang. The standard model assumes a period called inflation, an extremely rapid expansion in the first tiny fraction of a second, seeded the initial density variations that eventually grew into galaxies and the cosmic web. Tweaking the details of inflation can alter which structures form first and how fast they grow. Some inflationary models produce more power at small scales, which could allow faster galaxy and black hole formation without changing the rest of the model. None of these ideas is yet proven. Each makes specific predictions that Webb and future telescopes can test. The next few years of Webb data, combined with results from ground-based surveys, will rule some of these out and strengthen others. Physics is at the edge of something, a new understanding of what the universe is made of and how it works, waiting for the confirmation that tips one of these theories from speculation to established science. And Webb is still running, still staring into the dark, still finding things nobody expected. Webb was designed to last at least 10 years. It launched in December 2021 with enough fuel to maintain its orbit for significantly longer. Current estimates suggest it may operate well into the 2030s. The discoveries it has already made would fill decades of scientific literature. What it finds next may change the conversation entirely. Several major programs are already underway. The deepest survey Webb has yet attempted is currently accumulating observation time. It targets a region of sky even smaller and deeper than the original deep field image, stacking hundreds of hours of exposure to detect the very faintest, most distant objects that exist within range of Webb's instruments. The goal is to push the detection limit back further in time, closer to the era when the very first stars and galaxies switched on. Scientists believe Webb can reach objects from just 100 to 200 million years after the Big Bang if the survey runs long enough. Those objects, if they exist, would be unlike anything detected so far. They would be the true first generation of luminous structures in the universe. A separate program is systematically hunting for direct collapse black hole candidates. The theory predicts specific signatures in the spectra of early objects, particular ratios of emission lines that distinguish direct collapse black holes from black holes that formed through standard stellar evolution. Teams are building spectroscopic catalogs of thousands of early galaxies and running them through automated searches for these signatures. Even a handful of confirmed direct collapse events would transform our understanding of how the most massive black holes got their start. Webb is also being used to study the intergalactic medium, the diffuse gas between galaxies, in more detail than ever before. The reionization history of the universe, the process by which the cosmic fog was cleared, is encoded in the absorption patterns of distant quasar light as it passes through this gas. Webb is measuring those patterns at redshifts that were previously inaccessible, building a timeline of when and where reionization happened and which galaxies drove it. Closer to home, Webb continues to observe solar system objects. Upcoming programs will study the atmospheres of Mars, Venus, and the ice giants in unprecedented infrared detail. Webb has already detected carbon dioxide in the atmosphere of an exoplanet. Future observations aim at detecting water vapor, methane, and oxygen in the atmospheres of Earth-sized planets orbiting nearby stars, the chemical signatures that might indicate biological processes. That final goal is the one that draws the most breathless attention. Finding a biosignature, a chemical fingerprint of life, in the atmosphere of a distant world. Webb cannot confirm life on its own. The signals it detects would need corroboration, but it is sensitive enough to detect the right atmospheric gases, and the exoplanet programs are now pointing it at the best candidates. Every answer Webb finds opens a new question. Every structure it discovers reveals a gap in the models that describe it. The telescope has already shown us that the universe built itself faster, stranger, and earlier than we understood. It has broken the timeline of cosmic history and forced physicists to confront the limits of the best model they have ever built. And it is still out there, 1,000,000 miles from Earth, mirror open, cooling in the dark, staring at the edge of time, waiting for the next thing nobody expected to find.